Okay, thank you. Okay, let's now pivot to the third part of our research presentations. Power grid and e-mobility, low or zero carbon fuels, and distributed energy resources, DERs. First presentation is lower grid emissions and better grid performance.
Okay, hello everyone. My name is Ben Leibowitz. I'm an associate professor in operations research and industrial engineering, and I'm going to share some work that I did with Professor Kara Kockelman from civil architectural and environmental engineering. She's right here in the audience. And this work was really led by our former postdoctoral researcher, Bala Sambasivam. And really the goal of this project was to look at smart charging programs for electric vehicles, where the idea is to cede some control over when electric vehicles charge to the utility so that they can coordinate EV charging with the electric grid and charge the vehicles at times when it's economically and environmentally beneficial to the power grid for the EVs to charge then. So some of our research questions are listed here. So how large are the economic in terms of dollars saved and environmental in terms of emissions avoided? The benefits of EV smart charging programs. Then one question we had was how much of the overall benefits result from modified electric grid operations, so dispatching the plants differently because the EVs are smart charging, versus avoiding investments in additional capacity in the grid because you're able to manage these EVs as a flexible load. On the investment side, which particular investment needs are reduced most because of EV smart charging programs? And then these benefits are not necessarily going to be the same depending on where you're smart charging these EVs. So in what regions of the US are the benefits particularly large or small? So in terms of our methodology, it consisted of several different components. So first, we had two different scenarios for EV adoption. The tempo scenario is based on an NREL projection of EV adoption from now over the next several decades. So that's more like what we, or at least NREL, expects to happen. The fast adoption scenario is not really realistic. It's more sort of a stress test of imagine we adopted EVs as quickly as possible, threw them onto the grid. Can the grid handle that increase in load? And how much would smart charging help the grid actually accommodate that quick increase in EV charging demand? And then the smart charging program designs we considered, these were actually synced up with a survey that one of Kara's other PhD students worked on to try to actually understand people's willingness to participate in these programs. So we had sort of two opposite extremes, which are unmanaged charging, so people just charge whenever they want to, and then fully managed charging, which is where the utility controls the entire charging schedule. And then in between, we had daytime and nighttime smart charging programs with different modeled participation rates. So we impose constraints on when the vehicles are able to charge, and then within those constraints, right, the utility has the ability to schedule the charging. So then we ran these scenarios in a large US-wide capacity expansion model called READS. So this is a tool that's open source. It's developed by NREL, and we made some extensions to the model in order to represent these smart charging programs and see what effects they have. So the decisions in this large optimization model include what types of investments to make in the grid, generation and transmission, and also how to operate or dispatch the system in each model period. So just a few quick highlights of our findings. So the first finding is that in monetary terms, the emission cost savings, so we're sort of converting them all to dollar values, are relatively small, I guess you could say. Although remember, this is not EVs versus non-EVs. This is if you have a lot of EVs, what's the difference between smart charging them versus the default charging? We get $150 roughly per EV over the long run. Those are sort of the emission cost savings per vehicle. We found that the nighttime smart charging program is more beneficial than the daytime program. The electric grid cost savings, they're a little over 2%. That sounds fairly small, although again, we're just talking about scheduling EV charging. So we're not talking about EVs versus no EVs, differences in generation, investments across the board. This is just due to EV smart charging. So in absolute terms, that 2.3% is fairly large, so $61 billion in net present value terms. So one interesting finding is that actually the most notable benefit, or I guess mechanism through which these benefits arise, is that the EV smart charging programs reduce the need to invest in battery storage, especially as more solar and wind come on the grid. You can see, for example, in the fully managed charging scenario, relative to the unmanaged charging sort of baseline, you only need about half as much battery storage because you're able to use the intelligent scheduling of EV charging to balance variation over time in solar and wind generation. So the fact that actually a lot of the savings come through avoided investments rather than necessarily just grid dispatch highlights the importance of using a capacity expansion model and not just a production cost model to understand these benefits. And last finding I'll highlight, regionally we find that the benefits of smart charging are largest in central regions of the US where there's a lot of wind generation. There's still coal to displace from the mix. So if you can shift the charging from the daytime to the nighttime, especially to burn less coal, take advantage of that cheaper and cleaner wind, the benefits per vehicle can be particularly large. So I'll stop right there and just say, please feel free to see us at our poster to talk and learn more. Thanks. Yeah.
Thank you. Next is toward equitable transportation electrification in Austin, Texas.
Bueller.
What's the slide next? Cool. Hello, everyone. My name is Tigris Mendez, and I am with the UIL lab. My coworker, Sunjun Choi, he worked with me to work on this investigation of equitable access and EV adoption within Austin. So our principal question was, who owns Tesla? We investigated the relationship between vehicle adoption and regional characteristics in the Texas Triangle. Initially, we wanted to find our EV registration counts, which were provided by the Dallas-Fort Worth Clean Cities program in 2022. And we were also able to find MSRP data as the closest data source that we could find to do a elasticity price comparison. We found through this EV registration data that 59% of EVs in Texas were Teslas. And as you can see from these three predominant regions within the elasticity graph, that there were some significant signs of price utility that pushed people within different price ranges of being able to afford EVs to purchase. And this is possibly due to Tesla's influence with their brand utility. As far as the chart on the right, or the map, we can find that there's significant segmentation of EV adoption, especially around Texas Triangle cities and the border cities. The method that we used for analysis was primarily PCA, to understand the variance that we had in different parts of our data. So we did first our PCA variance, and then we removed our outlier and we used these three different analysis techniques, machine learning techniques: k-means, hierarchical clustering, and affinity propagation. We used silhouette scores on the right side to compare each of the models using 2 and 3 clusters to understand how the data was reacting with these models. And with our goal of highest silhouette score, we chose hierarchical clustering for the rest of our analysis. With 2 clusters, we primarily found that there was only a segmentation of urban centers and non-urban areas within the Texas Triangle cities. They did have a higher silhouette score, but they did not show us as much granularity of the EV registration data, demographic data, and price analysis data that we hoped to find. So on the bottom, we found that the 3-cluster model, or using 3 clusters within the model, yielded a separation of urban centers and revealed to us that the EV adoption mirrored demographic conditions. Finally, we found that charger installation within urban centers was most prominent, while the outside regions of Texas cities did not have as much charger installation. Focusing on the cluster C, as you found on here on the outskirts, we found that non-Hispanic white population, married households, higher income, and higher education levels, and so forth, were most likely to have more varied amounts of EV registration and pricing. They did not tend to go to one specific brand, but would go across the whole spectrum. While in the centers, lowered price EVs were more prominent, which indicates that people who live in the cluster C on the outskirts are likely to be home charging. The most important takeaway of this was that EV adoption is predominantly with higher income and non-minority groups, while people who are lower income and minority groups are not adopting. And we would like to see further investigation into how Tesla impacts this in the market. Thank you.
Next, advanced algorithms for optimizing electricity demand for electric vehicle fleets in Texas to support the grid and local communities.
Hello, my name is Paula Acevedo. I'm a master's student, and I'm going to be presenting our study where we have 2 main objectives. The first one is looking at the grid capacity with the increased electricity demand with new electric vehicles in 2030 and 2050. And number 2, we are looking at the future placement of these new charging stations placed equitably throughout the city. And I'm going to focus on the second one. And why are we studying this? The Austin Climate Equity Plan aims for a 40% of vehicle miles traveled being from electric vehicles in 2040. And this will add demand to our grid. And with this, we need new charging stations that need to be placed strategically and equitably throughout the city for a just transition. And not having an equitable placement can perpetuate inequalities in communities, and they can also delay the adoption to new technologies. I'm going to go through our methods and data and some of our results. We start with, on the top, you can see the map of Austin. We are using the resolution of census block groups. And we are conducting an evaluation process using additive weighing in each of the census block groups. So we have a baseline equitable placement scenario where we assign equal weights to the different indicators you can see on the second box here on the left. We look at the number of jobs, number of residents, number of students in each census block group. We also look at the number of trips by households in each census block group, number of trips starting and ending from ride-hailing services. We look at the current charging station density, DC fast charging current placement, and other indicators such as walkability, PM 2.5, and for the baseline equitable scenario, we look at equal weights. After conversations with City Council and Austin Energy, we looked at the priorities they have for future placement, and we looked that the resolution from City Council addressed that multifamily buildings should have a level 2 charging station in a 4th mile from the building. So we are looking at scenario 1 of multifamily housing density. We look at the number of units of multifamily buildings in each census block group, and we get a density from that. And this one focuses on level 2 charging. Then we have scenario 2, city-owned land density. So we look into the number of parks and number of Austin public library locations throughout the city. This to reduce costs when installing DC fast charging stations in the future. And with the scenarios and the other indicators we're using, we obtain a ranking of EV charging station future placement. So we get a score for each census block group, and we obtain the top 50 locations. After this, we look at the top prioritized locations, and we overlap that with the Justice 40 mapping and the DOT disadvantaged community, and we identify the locations that are prioritized and that are also a disadvantaged community to conduct a qualitative study, do some community outreach, listen to the needs and concerns of these communities for future adoption EV charging station placement. And some of the results you can see here is scenario, which is the baseline equitable scenario on the left. The yellow colors are the top 50 prioritized location in each of the scenarios. And on the left, you see the baseline equitable scenario. The letters moved a little, but the left one is the baseline. You can see that there's a distribution throughout the city. Then we can see the multifamily density scenario and level 2 charging, that you can see that it's more distributed in the surrounding areas of Austin. And finally, we have the city-owned land scenario with more concentrated prioritization in the center of the city. With this, we obtain a framework for future decision policy analyses, and so Austin Energy can have a framework to decide where to install future charging stations. And future work, we're going to conduct the community outreach, and we are also looking at the current placement inequity index in the city, but we can speak a little bit more about this on the poster presentation. Thank you.
Next, a modular and flexible DC to AC converter cell for future grid systems.
Good afternoon, everyone. I'm Kamakshi, a PhD student in Texas ECE. My research topic is a modular and flexible DC-AC converter cell for future grid systems. Let me give you all some background on this topic. So what grid utilities want? They want to interconnect different AC grids. They want to increase their transmission capacity, and they want to integrate renewables. But how do they do that? They usually use high voltage DC current systems, aka HVDC systems, to do this. So the first HVDC system in the United States was built in 1932, and it had a power capacity of 5 megawatts with a voltage rating of 15 kilovolts. Fast forward to 2010, the Transway cable happens to be the first MMC in the Western Hemisphere with a voltage rating of 230 kilovolts and a power rating of 400 megawatts. These numbers are increasing day by day, with the most recent MMC project to be around 5,000 megawatts and 600 kilovolts. So how are we doing this? How do we achieve this? For this, HVDC systems use multi-level converters, which involve power electronic devices, which are switched in a certain fashion to get the AC to DC conversion. Conventionally, modular multi-level converters are used to do this. So what happens here is we have multiple sub-modules in which there are different semiconductor devices, and these sub-modules are controlled using a central controller. What the central controller does is it gathers data from every sub-module and it will send command to every sub-module. But what happens in conventional MMCs is because of the burden on the central controller, the resiliency decreases and it becomes less scalable. Also, it uses hard switching techniques which reduce the switching frequency and decreases the efficiency. What we have proposed is using a decentralized modular multi-level converter. In this, each submodule will have its own local controller which will govern the functioning of every submodule, and we will be using soft switching circuits. The topology involved will be auxiliary resonant commutated pole circuit. This will help us increase the frequency and we'll achieve very high efficiency which are needed in HVDC systems. We have got promising results from our control structure. Snapshots are pasted on the slides, more on this in my poster. Also, the next steps would be designing the hardware and actually implementing the control on our hardware. We aim to do this by this summer, so it will be exciting to see how the hardware turns out and if our control is more reliable than the conventional one. Also, what we aim to do is we want to reduce the energy storage requirement of each sub-module, because conventionally in the sub-modules which are used, there is a topology which is called as a half-bridge inverter circuit. It utilizes capacitors which are double the size of the actual hardware. So we want to reduce the energy storage requirements by 50% so that the space required for these large complex systems will decrease. And thereby, we want to make the system more reliable and scalable and efficient. More on this on my poster, so do visit my poster. Thank you.
Thank you. Next is high-rate, large-area deposition of magnetic materials for the next-generation energy technologies.
Hi, everyone. My name is Elaine Ng. I'm a PhD student advised by Dr. Alex Hansen and Dr. Jean-Ann Incorbia in the Chandra Department of Electrical and Computer Engineering. And today, I'd like to share our work in developing a high-rate, large-area deposition system for magnetic materials, specifically in the application of fully integrated on-chip power converters. So on the left here is a typical power supply. This is like an NVIDIA GPU. I've highlighted in blue boxes all of these discrete wire-wound inductors. And these inductors are typically fabricated on separate chips away from the main circuitry. And in most power supplies, these discrete inductors are bulky, they contribute the most amount of losses to the system, and yeah, they're really large too. So in our project, we're trying to enable large-scale production of an alternative way to make magnetics, on-chip magnetics, which is some examples are of the on-chip inductors on the right. So integrating magnetics can drive down the cost and size of power electronics in general and enable higher efficiency and more modular power delivery systems. And efficiency and modularity being important requirements for energy relevant applications such as controlling super complex PV systems or driving really small IoT sensors for like studying climate. So the challenge with on-chip magnetic components today is kind of a one trade-off. Generally, depositing core materials that are easier to deposit, they're faster to deposit, like with materials such as metallic permalloy, they typically, in actual inductors, perform worse. They're usually very lossy. And on the other hand, core materials that have good properties for power conversion typically need to be deposited with processes that are slow and expensive. So in our project, we're focusing on a really promising core material for high-frequency power conversion. It's cobalt zirconium oxide. In the literature, it's supposed to have these amazing properties for high-frequency power conversion, but there's two catches. One, like many core materials, it's typically sputtered at very slow rates. And the second is, in order to achieve all these nice properties that we want, the deposited films have to have this complex nanostructure that you can see in this TEM image. It consists of these nanoscaled cobalt grains separated out by this amorphous zirconia matrix. So for our project, with our collaborators at the Southwest Research Institute, we've developed a DC reactive magnetron sputtering system for cobalt zirconium oxide. And I wanted to highlight that it includes a controller for the oxygen flow into the main sputtering chamber, which allows us to precisely fine-tune the film stoichiometries and also reduce the level of poisoning on the targets themselves, which helps us actually achieve incredibly high rates, deposition rates. So finally, I kind of wanted to show some of our results so far. We've gone through several rounds of iteration. So first, our sputtering system today can sputter cobalt zirconium oxide films at rates that are much higher than those in literature. And here I wanted to compare to a specific study. This is a study done by Harburg et al. At Dartmouth, and they were trying to fabricate on-chip inductors as well with cobalt zirconium oxide. And using their system, it took them 29 hours to deposit one of the layers that you can see in the inductor here. With our system, it would take just under 5 hours. Besides being a lot faster, our system can actually produce films with good properties. So on the right, these are two measured hysteresis loops, one of our samples and one from the Harburg study. Just so you know, the area inside the hysteresis loop is lost for inductors. So what we're trying to do is minimize the area of these hysteresis loops. So you can see that using that metric, our sample in blue has a much thinner, lower area loop, which indicates that it's lower loss than even Harburg's. So with these promising results, we're working on still optimizing the cobalt zirconium oxide material, but we're also thinking about actually making on-chip inductors now. And if you want to hear more about that, please come to the poster session. Thank you.
Next, manufacturing of high-strength nanolattice coating for cryogenic liquid hydrogen fuel storage.
So good afternoon, everyone. I'm Vijay.
I'm Peter.
So we are going to present on the topic of manufacturing of high-strength nanolattice coating for cryogenic liquid hydrogen fuel storage. So there are like existing state-of-art cryogenic techniques which are used to store hydrogen in storage tanks, but there's a problem of hydrogen boil-off, which basically refers to the vaporization of hydrogen into its gaseous phase from its cryogenic liquid state. So there are like existing techniques involving white paint coating or multi-layer insulation, which can still have about 15% of absorption, as you can see from this left-hand side bottom image from NASA's report. So what we are trying to develop is a graded nanolattice, which can have greater than 99% of reflectivity of solar spectrum from 0.3 microns to about 3 micron of wavelength, and also have ultra low thermal conductivity, which is less than 0.001 watts per meter per Kelvin. So on the right-hand side image, we have shown a design of our broadband reflector that we are proposing. Really high reflectance, greater than 90% from the wavelengths of 500 to 1500 nanometers. So coming to the fabrication of these multi-layer 3D nanolattices, initially we use a silicon substrate over which we place photoresist, and then we pattern hexagonally close pack nanospheres on top of these photoresist using lithography process. Then we subject it to atomic layer deposition, which is a conformal coating of aluminum oxide on top of this 3D intensity patterns that are formed. And over that, we place photoresist on top of it to provide a stable base so that the subsequent layers can be stacked on top of it. And over the photoresist, we again place a solid layer of titanium oxide, which results in the formation of figure D from the left-hand side image. So you can see there are like two layers now, one a porous aluminum oxide lattice and a solid layer of titanium oxide lattice. So these two have different refractive indices. The porous aluminum oxide has index of about 1.06, and the titanium oxide has an index of 2.7. So this high refractive index mismatch will lead to really high reflectivity across a broadband spectrum. We can keep repeating these processes in order to stack multiple pairs of aluminum oxide and titanium oxide on top of each other, and finally remove the resist in order to reveal the porous nanolattices. So on the right-hand side, you can see some SEM images that we have of the samples that we have fabricated, consisting of different lattice heights from 200 nanometers to 800 nanometers, with which we can vary the wavelength in which the peak reflectance is observed. We have also successfully fabricated 2-stack and 3 stacks of lattices, as seen from the SEM images over there. Coming to the optical characterization, we used a Carry 5000 spectrophotometer in order to characterize the reflectivity versus wavelength for the visible spectrum for now, from 400 to 700 nanometers, as you can see from this image. And as you can see, compared to the 1 pair, the 3 pair lattices have way higher reflectance for a really broad band compared to that of 1 pair of lattices, which is because of the refractive index mismatch that is generated by multiple layers which are present.
So I'm in charge of thermal characterization. So typically with these small features, standard thermal characterization techniques such as TDTR or laser flash or the hot plate method can't really apply here. So we're developing a new technique to measure the thermal conductivity. Here we utilize Raman thermometry. So there are different materials where they provide a Raman signal based upon their lattice vibrations. And then based on the features of that signal, we can extract an effective temperature of the object we are probing. So in our case, we deposit a graphite flake. So you can see that center image over here on top of the nanolattice. So you can clearly see where there's that nice porous nanolattice that VJ makes for me, and then those little pores that are just the underlying lattice. We shine a laser light on it, and then based upon our extracted temperature and the laser power we are exciting the material with, we can extract a thermal resistance. In our current model, we model it as 1D, and because it should be an ultra-low thermal conductivity nanolattice, that conductive thermal resistance will dominate the circuit. So we can extract an effective thermal conductivity, which at the moment we are measuring 0.042 watts per meter Kelvin, which is still pretty low, but there is more thermal characterization to work, and we're happy to talk to you guys at the poster presentation above. Or upstairs, yes. Not above. This is, anyway, thank you. Thank you.
Next, analysis of Permian Basin clean ammonia production, distribution, and market demand.
Hello, everyone. I'm Carrie Maynor, and I'm going to be presenting the work our team is doing on ammonia production from clean hydrogen in Texas Permian Basin. So to start, I will highlight why we're interested in ammonia. So as some other presenters have mentioned today, ammonia is being looked at as being a low or zero carbon fuel, as well as potential hydrogen carrier. But also importantly, ammonia is a critical backbone in the fertilizer production industry, which we know the big agriculture industry relies on heavily to produce the food that we've come to know and love in our local grocery store. So with this importance of ammonia in today's economy, it's important that we look at how we can decarbonize this process industry as we look to decarbonize most industries. And to look at this, we have started by building a process model and a process simulator to produce this ammonia. We have also looked at some economic analysis, particularly the LCOA, or the levelized cost of ammonia for the project, as well as the net present value of the project at a 12-year period. So future work will be to further investigate the distribution and transportation networks, as well as quantify some of these emissions benefits and the local demand of ammonia in the Permian Basin. So to start, I will talk briefly through the process model we've built using Aspen Plus, which is a very common process simulator. Fundamentally, to form ammonia, you just need nitrogen and hydrogen over an ion catalyst at a high temperature and pressure. We have modeled a plant that has a daily capacity of approximately 1,300 metric tons. And importantly, I want to highlight the three cases that we're simulating here. Case one being an ammonia production facility that is powered by natural gas. And what I mean by that is that in the left bottom corner, you see the power generator section. So we're using natural gas as a fuel source to provide all of the power that is necessary for this production facility to run. And a part of that, we have installed a carbon capture unit that captures 99% of the carbon that is emitted by burning that natural gas. Case two has some on-site power generation using heat steam recovery generator, but by and large, we are powering it using renewable energy purchased from the grid. And then case three, which is quite similar to case one, that has all its own power generation. Rather than using natural gas, we're using hydrogen as its fuel source. And so with those three cases in mind, let's look briefly at some results here. First, I'll start with the project cost. These numbers are from the Aspen Technology Suite. They have a process economic simulator. So as you see in the pie chart, the biggest cost right now we have is for the equipment cost and then the installation of that equipment. And so those two are the most important factors we have to make sure we get right. Otherwise, our project might not be feasible. And so a lot of care and attention has been paid to sizing the equipment properly. The next two metrics, which are the levelized cost of ammonia and the NPV of the project at a period of 12 years, we're using a hydrogen price of $2 per kilogram to represent a green hydrogen production facility that is utilizing a production tax credit. And so we want to use that as kind of our baseline case. An interesting result is that the NPV of the natural gas powered case with the carbon capture has the highest, even though it does have the highest project cost, and that is due in part to the 45Q tax credit we're able to take advantage of by capturing and sequestering that carbon. And then even though case two and case three do have a lower NPV, they're still feasible, and that is highlighted in the figure at the bottom right of your screen, where you can see over the previous 12-month price of ammonia is in that shaded region. Our three models do have some flexibility in terms of what price we can pay for the hydrogen and still have a competitive LCOA in the market. I'd love to get into this more in detail with you during the poster session, so please stop by. Thank you.
Next, microbial reactions during underground hydrogen storage.
Good afternoon, everyone. My name is Krishna Panthi. I'm a research scientist, and Dr. Kishore Mohanty is the PI of this project, and Dr. Owen Sung is co-PI of this project. So I'll talk about microbial reactions during underground hydrogen storage. So here, DOE has this concept about the net zero energy systems. So here, hydrogen is the main energy source, main fuel, and this hydrogen, can replace gas and oil. And to have this system, we need to have large amount of hydrogen. So we need to produce large amount of hydrogen, and as hydrogen is the lightest one, the challenge is how to store. So we should have like short-term storage as well as long-term storage for hydrogen. So to storage hydrogen, basically, most of the time, people are working on underground storage. We need to find big, space. So for that, we have started to work on the cavern, storing in cavern in collaboration with Sendia. And for that, Dr. Espinoza from CPE is the PI, and we already started on this project. We are also working on the storing of hydrogen in permeable reservoirs, such as aquifers and depleted gas and oil reservoirs. So here is the example of depleted gas reservoirs. So in this picture, so this is, aquifer and no hydrogen. We can, when we get more hydrogen, we can store here, we can inject here, and after injection, you can see hydrogen here, and when we need hydrogen, we can produce. So there are basically three different kind of, way hydrogen can be, like three challenges basically. Hydrogen can be consumed. So our hydrogen can be lost. So one is when we take out hydrogen from this reservoir, so the water present in that reservoir can absorb some of the water, some of the hydrogen. So, but that is only for cycle. After that, hydrogen won't be consumed. That is one challenge. Another challenge is hydrogen can be lost by abiotic reaction or geochemical reaction. We have been working on this, geochemical reaction. For that, we work with 4 different kinds of rock by injecting hydrogen gas at 80 degrees Celsius under more than 2000 psi and heating for 4 months and 8 months. And we analyze the rocks, but we didn't see any significant change. And literature, as we look literature, so mostly abiotic reaction can occur beyond 200 degrees Celsius. And most of the storage, people consider they are less than 200 degrees Celsius, they should be lower temperature, that's why that won't be really problem. But the main challenge is microbial reaction, because microbial reactions, they are ubiquitous, they can occur at any temperature. So that's why we are working, in this project, we are working on microbial reactions. So for hydrogen storage. So for that, we received 3 different reservoir samples, sac rock water and inospec, and we analyzed 2 water, and we identified different kind of bacteria there, and we specified basically bacteria which are in large amount, and we are analyzing and we are studying them. At the same time, we are studying, so what's the effect of hydrogen and without hydrogen in small accumulator, and we studied for 2 months, but the results, pressure difference with and without hydrogen are not that significant. That's why we can't conclude anything from this experiment. And this is the literature, this is from literature. Basically, these are the most important microbial reactions, and we thought first 3, methanogenesis, H2genesis, and sulfate reduction, they are relatively more important. That's why we got 3 different bacteria, of this, and we are analyzing, we are studying these bacteria, so in this produced water. And Dr. Song's her lab, has micromodel, and that micromodel has the ability to see the activity of microbes, or activity of microbes can be imaged or can be captured. So that micromodel is very long, like roughly about 1 feet long and 2 millimeter wide. So serpentine structure, and basically what she studied already is like calcite depositing microbes. So, and with time, she studied like microbial activity, how much calcite is deposited there, and these micromodels can be probed with Raman spectra to see what kind of bond is forming there. So we want to study our hydrogen producing as well as acetate formation or sulfate formation kind of bacteria in a reservoir brine, how they work or how they function. So from there we want to we ultimately, after doing bulk test and figuring out exactly, in reservoir brine, we want to study in core flood experiments. So basically, we don't have much result by now, but we are studying on that. So thank you so much.